you know, she'll just walk in the middle of my talk.
They look
So
like disapproving, so we like.
all right, let's get started. So Lynn is going to walk in with a bunch of drinks at some point, which is why I waited, but it's fine. So just before I start this talk, this is not the color palette that I intended. The projector has seemed to invert it, so I may have to stop and explain what the colors are supposed to be.
Everyone take your glasses and
All right, welcome. Let's get started.
There's no 3D action at all.
Yeah, see that India? That's not the color of India. It's a reddish. This is a more bright blue. Maybe everything's blue. All right, so I'm going to talk about space-efficient runtime tracking. Okay, so this is supposed to be a diff in GitHub. And these pluses, you can imagine you have the green bars that you normally see. There's pluses here. So this is code. This is a diff of moving an untyped program to a typed program. If you've ever used any sort of type system, you're familiar with a top-level annotation. This is any optional type system that you have to use. You have to go from having nice code that just seems to work, and for some reason you have to add these things. So there's a big problem here, and it's that someone wrote this manually. They had to take this working program, take time out of their day, and figure out what to write here, what syntax. You know, there's a lot of parens, and there's quotes and stuff. So there's a problem here. So the solution that we propose is to automatically generate and annotate your programs for you. So instead of you having a pull request full of your, 2 hands on the keyboard, it's run my tool, and I will give you all of the work for you. So our approach in a nutshell: first we instrument the program, then we observe the running program, and summarize the execution in a type annotation. So let's break that down. Okay, let's. Oh, that's a horrible color. That's green.
You just pretend that it's
beautiful.
Tell us all it's green.
So we're going to draw an analogy. So this is a megaphone. Let's say a megaphone is a function. So what's its input going to be?
vibrations.
Yeah, so some sort of noise, vibration, and what's its output going to be?
Enhanced.
Right. Excellent.
Somebody else came and took a drink.
Oh, really? Oh, well. Okay, so this is our megaphone. We're going from, a megaphone's a function, takes noise, emits bigger noise. Okay, so let's say that this is a function, so we need to write a top-level annotation for it. So let's try and categorize this megaphone using our approach. So what's the first thing we do? We instrument the megaphone. So we're going to observe what goes in and comes out of the megaphone with microphones. So the next thing we do is that we observe the running program. So we shout into the megaphone, and then we're going to record what happens at the input and on the output. But the program will otherwise run as normal. And then we'll get our recordings from our microphones and summarize the execution. This is kind of where the analogy breaks down. The megaphone is in D major, and the trumpet today is in G major. Maybe you were playing some Bach or something. I don't know. So what this talk is going to be about is kind of getting us used to how to track the behavior of different kinds of things. And we're going to talk about programs more than musical instruments. And in particular, this case here where we append things. And you might notice that there's a type error here. Because, the input here is wind, and the output here is... But this is a dynamically typed program. This is kind of indicative of what actually happens. We take a dynamically typed program. Who knows? We could have a coercion from noise to wind. But the point here is that we have redundancies in our recording. We've taken all this effort to record the output only to record it as the input all over again. So this is the flavor of what we're going to get out of this talk. Actually, any questions about that part? Okay, good. So now for something completely different. We're going to set up our example. ClojureScript compilation. What is ClojureScript? ClojureScript takes Clojure data and spits out JavaScript. So here's a couple of very trivial examples. Clojure data, numbers, JavaScript, numbers. And if we want to compile a list, a quoted list, we have to call the JavaScript function clgs call list and use an infix, or postfix, or whatever, parenthesis, and then recursively compile. Right. So we're just going to have a look at the compilation lifecycle going from Clojure forms to JavaScript strings. So the first step is the analysis phase. We go from Clojure forms to a more consumable abstract syntax tree that is going to dispatch on the op key. Every one of these AST nodes has an op key. So this is a value, this is a list. You might imagine there's functions, there's invocations, but we're just going to have values and lists here. So the second phase is going from this AST representation to a string of JavaScript. And this phase is where we're going to apply our approach for instrumentation and generating an annotation. So let's jump in. So this is the emitter. It's a function that takes in an expression, our AST, and spits out some JavaScript, it's a string. And this is kind of documentation purposes. Let's pretend this is untyped. And yeah, so basically the way this works, it dispatches on the op key, looks up the op key. If it's a value, well, we call the emit value helper function. If it's a list, we call the emit list helper function, which presumably is calls emit again, and yeah. So,
and those helpers don't really do any instrumentation per se.
Let's hold that question. Good question. So the way we instrumented our megaphone, remember, was to set up a microphone at the inputs and outputs. So when we do that with a function, what we naturally get is that we set up our microphones at the argument positions and at the tail positions. So, so whenever we call this function, we will record what the arguments are and what the return values are. So
I think I'm really confused.
Mm-hmm.
I thought you were going to omit instrumented code, but I think instead you're trying to instrument the emitter.
I'm sorry. So let's say today I decided to convert the ClojureScript compiler from untyped to typed. This is the scenario. I apologize.
Okay, I'm now with you.
I was like, I need some real code to apply my approach to.
Right, so what we're talking about, this is the data, this is the input to
Yes, exactly.
Okay.
Yes.
But it happens to be that your example is also a translator.
Oh, yeah, okay.
Okay.
Yes,
That's
exactly.
beside the point.
This is one of the classic PL problems.
Yeah.
Your prime example for how good programming languages can make your life easier is building more programming languages.
Yes, indeed. Guilty.
Great. We didn't say that at the specialization meeting.
Yes.
Jeremy and I had a meeting today in which we talked about all the value that students can get out of the PL specialization as undergraduates.
We're talking to the advisors.
We avoided
undergraduate
saying
advisors.
that it'll allow you to write metacircular towers of compilers that help you write more compilers.
Can you send an update after the meeting? Or?
Right, that was a horrible follow-up mistake to omit that.
All right, so hopefully, yeah, we have computer science solving other computer science and, the usual.
Okay.
So this is the example of the talk, and we're applying our approach to this example.
To this program.
Yes, exactly, to this program. So I was just describing how the inputs, we've set up microphones at the inputs, the arguments, and the outputs, the tail positions. But the microphones need to know one more thing, and that's where do they sit? And we're going to introduce a concept called a path. So a path is you can think of it as a path through data or functions. So here you can see that they grow to the right and you read them from left to right. So the way to read this is that when we record data at this microphone, we know that it's emits argument. And if we know more stuff, as we will in the next few slides, we're going to grow this to the right. And this microphone is going to record things about emits return value, and so is the other one. So let's look at a sample execution of emit. So we're going to call emit on an argument. And this is where things get interesting. Finally, we've got something to actually record. So we're going to set up our microphone because this is already instrumented. So let's imagine we've already called this function. We're going to set up our microphone to record this value as emits argument. So let's zoom into this. So this is the same data that we just saw. We're going to track it as emits argument. How do we do that? So we recursively, we sequentially go into each of the entries of this map like so. So the first thing we do is we set up a new microphone that records what's at the op key. And what we have to do is first extend our path so then this microphone knows where it is. And this is a keyword enclosure. It's an atomic piece of data. So we've got nowhere to go. So it's time to actually record some data. So we record what's called an instrumentation result, which is a pair of a path and a type. It says that down this path, we found this type. And this translation from a value to type, we're not going to talk about it. But you can see that it's kind of intuitive. And I should note that this val is a singleton type. So the next thing we do is we go to the next entry, and we extend the path to the items entry because it's the items. Now we've found that we have a vector. So we want to track a vector. So we go through each one of these and track its elements. So we set up a microphone here. We say, well, now we're looking at a vector element. Okay, well, we found a map. Well, we do what we did before. We recursively go in and check the op key. And then we see that it's a value. It's time to actually record the results. So we say, at this point in the program, we found this type. And similarly, if we want to track 1, we're going to see that it's the value entry, and also note that we found the type int at this particular path. Any questions?
Maybe to sum it up, what you've got a value, and then you have to distill types out of it.
Yeah.
Because right, one time you don't have types running around, one time you have values running around. And you wanna...
That's it. Yeah. All right.
Not to go too deep into the details how actually figures out this type, but do you need that path to figure out that one has type int here? Like, what?
Well, he's trying to figure out that the whole map thing that the one was encased in, this bigger value, what was the type of that bigger value? So like structured types.
So the path is more of putting the final type back together.
Yes,
than you
exactly.
This is a big purpose.
Well,
Can you
types are
imagine-
trees, right? Leaves,
Yeah.
and so you might have
Yeah, I
a
guess-
leaf, but you need the rest of the tree.
Can you
Yeah.
help me,
Paths are an
while
alternate
we're doing, can you
representation.
help me read this thing in the curly braces? This is a list of items, and where did the vector
This
come
curly
from?
brace, this is an associative data structure that associates the op key with list
Okay.
and items with this vector, which is this
Oh,
square.
okay.
Yeah, sorry, I should have said that. But yeah, if we reduce over these values, these instrumentation results, the idea is that we can recover the full type, the tree. It's just a kind of a strange representation of a type. Okay, so what's the problem? Well, as soon as we call this function, we completely traverse this data structure. And since we're instrumenting this entire program, this emit val is also instrumented. So what's going to happen is that we set up a microphone at emit val's argument position at this path, and then we completely traverse the same data all over again. So this is the first problem. We have eager recording. We completely traverse things, and what we get is this rich data. We get complete data about the kinds of things, the ins and outs of our functions. But this comes at a significant runtime cost, which we pay over and over again for perhaps the same data. And yeah, it's kind of a frustrating problem. Why are we doing this? So what's the solution? Well, a solution is using laziness, so lazy recording. So what this is supposed to make you think of, we have a microphone that follows this film clapper. When you say action, you record, and when it's cut, you stop recording. And this makes more sense if you think of us actually wrapping this value, and as the value goes through the program, the microphone goes with it. And at key points during the program, we say, okay, record, stop, record. So let's have a look how our program changes. So let's say we've instrumented our program with lazy recording. So at this point in the program, we actually wrap the argument. So because this is lazy, we don't actually do anything at this point. We haven't gathered any data, because why would you realize a lazy value unless you needed something? So at this point in the program, we don't have anything. This is a significant departure from the eager checking, the eager recording. So when something interesting happens is here, because there's an eager operation. We have to look up a value out of this map. So let's have a look and see what actually happens at this point. So we have this data structure that we've been looking at. The operation that we're going to have is we're going to look up the op entry, which is going to be list. But this whole thing is wrapped in a lazy recorded check. I keep saying check. A lazy recording. And it knows that it's emits argument. So as before, we check this value by taking the outermost path, appending it with the new information that we have about the new path element. And because this is an atomic value, we've now got some information that we can use, some data we can use about this program. And now we're done, because this is lazy, and the operation was look up the op key. So, yeah. So what's the problem with this approach? Well, as before, emit val is also instrumented. So what emit val is going to do, it's going to wrap its argument in a lazy check. And what we're going to end up with is something more like this. We have a wrapper wrapping another wrapper. So when we do an eager invocation, we're going to have to go through 2 layers of wrapping and have to, there's a lot less that we have to traverse, but we still have to reach in twice. And this is unbounded. Like this could blow your stack basically. And this is what's known as space inefficient wrapping. And let's just recap where we're at. So we've tried eager recording, we have lazy recording, and lazy recording gives you sparse data, but it's actually extremely relevant data. It's only data that your function actually uses. And you have a low runtime cost, but you still have some redundant re-recording. Yep.
So the data that you do traverse, does that get traversed twice in that example?
The op key would, yeah.
Okay, so it would still overall be less runtime, but there is some redundancy in the things you actually care about.
That's exactly right.
Okay.
Yes. And the problem is more that if you have 100 wrappers, your stack is going to be, much bigger. Yes, and it's unbounded.
Okay.
So yeah. Okay. So how do we fix space inefficient wrapping? Well, we use space efficient wrapping, and this is what space efficient wrapping is. We have this wrapper within a wrapper. The inner wrapper knows that we're going to record the values as emits argument. The outer wrapper knows that it's emit val's argument. So let's combine these two and record them simultaneously as coming from both of the places at once. So let's see how this works. So this speech bubble is going to tell you what happens. We're going to combine the inefficient wrapper to an efficient wrapper. Look at it go. Much nicer. So at this point in the program, no. So what we're going to do now, we're going to have a look at what this op operation is going to do on one of these, on a wrapped value with 2 paths. So we have a lookup on op. We're going to go to here, but we have a space-efficient wrapped recording. So as before, we go to this. We go to the first entry. We extend the first path, but we also extend the second path. And since this is an atomic value, we're done. And now we get 2 for the price of 1. We get 2 inference results for 2 different places in the program for just 1 pass over the data. And yeah, this would have taken 2 passes through the wrapper with space inefficient looking up. Okay, so we have our 3 approaches here. This is the latest one. We have sparse recordings in the sense that you only get information about what you actually try and get out of your data, or what the function actually uses, the components you use in your data. You have a low runtime cost, but with space-efficient wrapping, you get less re-recording. I'm actually not entirely sure how to say how much less, but it's when you have when you have this situation of direct wrapping, it eliminates that. So it's an interesting question. Like, is this strictly better for does this give us enough information to make to correctly categorize our functions? And yeah.
So lazy and space efficient always gives you the same amount of data as just lazy, right?
These 2 are the same.
Yeah.
Yes.
Yeah. So the question is just, is lazy enough in comparison with eager?
Yeah. Yeah. We can basically pretend that this one isn't here. This is kind of
You superseded the lazy with the
yeah,
space.
Yeah.
exactly. This is the naive lazy. This is the less naive lazy.
Now,
Yeah.
Yeah.
I guess one question I have is just how space efficient is it? So in the gradual typing literature, at least the first couple space efficient papers were all about trying to get down to a constant factor of like imagine that all your wrappers just went away, and how does your program executing without them compared to with them? And we were able to get it down to a constant factor, which was great. Now here, I mean, you're definitely way better off than with the lazy.
Yep.
I'm not sure if it's down to a constant factor yet or not. And even if that's achievable, I don't know. But that's something to think about. And it might, and I guess, I think we talked about this a little bit, but how much sharing is there or could there be with these paths? Because even though you got rid of one of these boxes,
Yep.
but you still have 2 of those.
Mm-hmm.
And in some sense that's necessary, but there's still, the space still grew for that. And so it's not clear to me.
In the sense of the space it took to store these paths.
Or here's another way to put it. Could you still get, let's say it takes n seconds to run your program.
Yep.
Could you still end up with O of n data necessary hanging around in the form of paths as a result of your
That's a good question.
right?
Uh-huh.
Or is it O of 1?
Yeah, so the usual way that these space efficiency statements are made is, 1, are there programs where the thing that's more efficient is asymptotically better in terms of space usage than the program that's the version that's less efficient? And I think that's clearly the case. We can stack up arbitrary amounts of emits, and the space-efficient one will collapse them all to 1. So we can have. But then there's the second one. There's a second question, which is the instrumented program with the efficient approach in the same asymptotic complexity class as the uninstrumented program, right? For space usage or for time complexity. And there's that's another interesting question. I think
Right, that's the one I was
it's sort of
wondering.
obvious that just the description you've given so far, it can't be in the same complexity class. You can have some program that runs in constant space that accumulates a ton of paths because it, say, has one function that calls 1,000 different functions, or it calls generates n different functions and calls them, and then that'll use order n space, but previously it used order 1 space.
But there might be some improved or sophisticated version
so there's a
that got rid of that.
So there's an interesting, but if that's in the answer, if the answer is O of n,
Then you can't do anything.
then you can't do anything
Right.
about it.
And then you sort of be like, that's fine. I mean, okay, that's just-
But
Where are we going
one,
to from here? I don't want to.
No, we're done.
one thing you might like is to say something like, this never consumes more space than the original program plus
this
never-
is the output.
the size of the output.
Okay.
Because that's sort of the best you can do.
Yeah.
But, and then there's other questions like, how do you, that we talked about in group meeting, like, these are maybe more efficient than you might expect in terms of space usage because you can share
Yeah.
data share structure between different maps and between different results.
Yeah.
Or different paths.
And how to consider that in thinking about the space usage is an important question.
And during group meeting, you said that like with this lazy space efficient, you're already getting like just in practice on a bunch of examples, you're getting some good performance, right?
That was like just going from here to here, like things were actually completing. Like and then things got faster when I got to here, but this was
That
the
was a
biggest
big
jump. Yeah. Yeah,
Cool.
basically.
That's cool.
All right, well, I'll let people thank me. All right, I'll take questions. Ryan?
Do you have any benchmarks compared to these approaches?
Nope. I did this last week.
Aside from some programs finished and others didn't, like, did you like anecdotally try this out on any big closure programs and experience?
Yeah, I've been working on the closure script compiler, like exactly this, and
So that's your benchmark.
yes, and
Okay, a related question is, are other people using this tool at the moment?
No.
Or are there plans to like eventually advertise this as something that you can use to retrofit your untyped code to type?
this is exactly what it's for. It's for mass consumption. And that's why I'm interested in actually getting it to work on real programs, not just the ones I've been working on all year, you know. So that's why I whipped out the ClojureScript compiler, which has enormous data structures that get pumped through it, basically. And yeah, that emit val and emit redundancy is like exactly what happens. You just get stuck at the argument of every function because you do it over and over. And you traverse things.
So it sounds like you picked a good sort of torture test.
Yeah, it's pretty brutal. Yeah, the interesting question is lazy too lazy to get good annotations from it? So maybe there's a combination. So one combination I've thought of that I haven't tried is you wrap everything lazily, but you asynchronously try and traverse as much as you can, but you don't hold up the program. And
Interesting.
yeah, well, it's kind of synchronous and asynchronous at the same time.
I wonder if you could even get to the point where you're showing the programmer the annotations you got so far,
Yeah.
and they could, and maybe there's still like a little fuzzy spot here, and
Yeah.
they could
Yeah, poke
be
it
like
more.
poke it.
Oh,
give me
yeah.
more, give me
Instantiate.
more.
Yeah,
Perfect.
That's cool.
Yes. All right. Next question, Roger.
Yeah, so I had a question between rich recording and sparse.
Yeah.
So the way that works is if you're saying that there's a function and it it doesn't like use some part of the data, it's not gonna put that in the type.
Yeah.
And the question is that like how much of that do you actually want, because the function is not using it, right?
It's a great question. Sometimes you could imagine someone just wanting to know what the major data structures are. Like, what are the, like say you had a configuration map that was through your program. You didn't care what a specific function took out of that configuration map. You just wanted to know what was in that configuration map. Like, then eager's a great, like, a great option. So you, like, one heuristic I thought of was if it's, like, you eagerly check like 2 levels of a map, otherwise you lazily check it, and then you could, yeah. But I haven't even started trying experimenting with this. So this is exactly the right question.
You said specifically, I'm not going to talk about this, so that's why I'm asking you to talk about it. How do you generate types from values? Because that's making me think about how much structure sharing you can get in various places, and if you can find the most general type for different runs. So can you talk about the various choices on the one end and how it might impact the results you're getting here? No is a perfect.
Well, it's a bunch of heuristics. So one heuristic is that closure programmers don't very rarely care about numeric singleton types. Like if there's 1, 2, and 7, it's an int, you know. But sometimes they do care, like to create enumerations, so enums. They have keywords. So that's why in the example we converted the keyword value into a singleton type. So we remembered, we didn't throw away that information. But remembering the numeric singleton type would just be garbage in terms of the end user, which is the closure programmer. And it's really what information do I want to keep around? And it depends on the programming language. And this is just some of the idioms in Clojure. You can imagine what it might be in Scheme or Racket.
So,
Yeah.
so like, an important part of this whole thing is what happens when you've got like multiple calls to the same function, right? How do you sort of deal with that? Like, do you just have lots of data all about one function in a big list that you then do something with, or do you merge that information eagerly, or what do you do?
So you basically can't distinguish between different calls.
In the way you've got it?
Yes,
Okay.
in the way that I have it. So
But what do you do? How do you collect all of it, like every single call? And that's like a big
right
list.
now, yes, exactly, yeah, and you end up with all these pairs of types of paths to types. Yeah, exactly, for every call.
Okay.
Yeah.
I could imagine if you were to sort of like merge that information eagerly, or merge it as it's created, because you sort of merge it at the end, right?
Mm-hmm.
But if you did some of that work as it's being produced,
Mm-hmm.
that might help you get even more space efficient.
Yeah, because the actual annotations at the end are going to be smaller than the number of inference results.
Right.
Like,
When I was playing around with some stuff related to this, what we did is, like let's say each time you called the function, maybe the input value gave you a type, but maybe it was a type that had like dynamic still there in places where you didn't really know yet, or whatever, and then we would, oh no, that's not true. No, you get these different types, and when you try to merge them, sometimes they're just like the same type, and then you just merge it,
Yeah.
right? But sometimes they might disagree with each other, and in the spots where they disagreed, that's where we just put dynamic in. So we'd always just have like one type there, but in the places where we had to, we would. But I guess you've got unions, right, and stuff like that.
Yeah, and
So it's not so simple.
I think that there's a way that there's a lattice that I follow, but it's not written anywhere.
Mhm.
It says things like it's okay to combine strings and keywords, but as soon as that position has a function, it's now any.
Mhm.
Like it uses the idioms of closure. This is another one of those.
So, but maybe applying that during the collection instead of after
Yeah.
might help.
Yes, I agree.
Though I don't know how to deal with recursion stuff. I know you do fancy stuff about recursion.
That all comes later, actually. So
Yeah.
your idea works, and it would probably deal with, I think, your speculation about the space efficiency. And then you can just traverse, you have the passes over it later, once you're done. So the types, in a way, I think are a more compact representation of the inference results. Like, I don't know how strongly to say that, but that's what my gut says. Yeah. Got, yeah. All done? Cool. Thank you.
Thanks, Sam.
Yeah, thank you, everyone.